Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 10th graders 2024, problem number 4. Let n be a positive integer. We wish to find all functions f from the set of real numbers into itself, satisfying the following equation: f of x plus y to the power 2n equals f of x plus y to the power 2n minus 1 f of y for all real numbers x and y. And a further condition is given, which will be very important, such that the preimage of 0 has exactly one element. So there is exactly one number, x, such that f of x equals 0. Exactly one. Here are my hints for this functional equation. First, set y to be equal 0 to show that f of x equals f of x. Then, take our original equation, change x to the power 2n, and use the symmetry to show that f of x to the power 2n plus y to the power 2n minus 1 f of y equals f of y to the power 2n plus x to the power 2n minus 1 f of x, and set y to be 1. Then show that f satisfies Cauchy functional equation, which means that for every two real numbers x and y, f of x plus y equals f of x plus f of y. And now, crucially, use our assumption to prove that our function is injective. It's injective by using Cauchy functional equation, and deduce that f of x must be equal x for all real numbers x. So give this problem a try, and I will see you in just a minute. Alright, so let's denote our functional equation by asterisk, and let's denote... let's do just that. First, let's set y to be equal 0 in our condition asterisk. Then we have f of x equals f of x. You know what? It's very important. This equation will be important later, so let's write it in different color. f of x equals f of x. Let's call this condition double asterisk. Alright. Now let's set something else. Or maybe let's rewrite our equation. Our equation asterisk becomes the following: f of x plus y to the power 2n. Instead of f of x, we can just put f of x plus y to the power 2n minus 1 f of y. Now, let's change y, or maybe let's change x to x to the power 2n in our condition asterisk. Then we have the following: f of x to the power 2n plus y to the power 2n equals f of x to the power 2n plus y to the power 2n minus 1 f of y. But also, notice that the left-hand side of this equation is symmetric. So we can change x and y, and we will get that this also equals f of y to the power 2n plus x to the power 2n minus 1 f of x. Alright. So we have this equation. Let's eliminate the middle part. We will not use it for now. Right. And now let's take this equation. I will call it triple asterisk. And let's set y to be equal 1 in this equation. So set y to be equal 1 in our condition triple asterisk. Then, what do we have? X to the power 2n minus 1 times f of x. F of 1 plus that equals f of x to the power 2n plus, well, f of 1 once again. F of 1 cancels, and we have x to the power 2n minus 1 times f of x equals f of x to the power 2n. And using this equation, we can rewrite our condition asterisk once again. Asterisk now becomes f of x to the power 2n, or maybe let's take a glance at our equation. F of x plus y to the power 2n equals f of x, and instead of y to the power 2n minus 1 and so on, we can write f of y to the power 2n. Alright, and now notice that this holds for any real numbers x and y. Alright, but observe this very simple fact that mapping which takes real number y and returns y to the power 2n, this mapping, this function has a range of non-negative real numbers. So we can rewrite our equation once again using this observation, and asterisk becomes the following: that for every real number x and for every y greater than or equal 0, f of x plus y equals f of x plus f of y, which is almost a Cauchy functional equation. But here we have this constraint and we don't want to have it. I wish to show that this equality really holds for every x and every y, and we can do it in the following way. We can prove it in the following way, that first of all, let's set x and y to be 0. In our condition asterisk. Then we can deduce very easily that f of 0 equals f of 0 plus f of 0, so f of 0 equals 0. And now let's set y be equal minus x in this condition asterisk. Then 0 equals f of x plus f of minus x, which means that and also maybe, you know what, let's be very clear. Maybe be clear, let's write that, let's set x equals minus y. Then this is the case for every non-negative y, which means that our function is odd, i.e. f is odd. Our function is odd. Alright, and now finally, let's do the following. Let's do the following. Let x be any real number, and now let y be non-positive, less than or equal 0. Then we can write the following: f of x plus y. Since our function is odd, we can write that it's minus f of minus x minus y. And now, minus x is any real number. We can write it minus x plus minus y. And now, minus y is non-negative, so we can replace it by minus f of minus x plus f of minus y. Alright, so we have minus f of minus x minus f of minus y, which is, using the fact that our function is odd, it's f of x plus f of y. So, which means that our equation holds not only for non-negative y, but for any y. Let's write it. We have demonstrated that, in fact, for every real number x and for any real number y, f of x plus y equals f of x plus f of y. Which means that our function satisfies Cauchy functional equation. Now, the most important claim, my claim is that f is injective. I claim that it is injective. Let's prove this claim, and we will be almost done. Proof is very simple. Suppose that f of x equals f of x prime for some x and x prime which are real numbers. Notice that then we have the following. What is f of x minus x prime? Well, it's f of x plus f of minus x prime. And now it's f of x minus f of x prime because our function is odd. Well, and now f of x minus f of x prime is 0. But notice also what is 0? 0 is f of 0. We have demonstrated that f of 0 is 0 right here. Alright, so, and remember, we have, now it's time to use our assumption. By assumption, the preimage of 0 has only one element. Has exactly one element, so this argument must be equal 0. So x minus x prime equals 0, i.e. x equals x prime, which proves my claim. And now we are done, almost, almost, because let's go back to the very beginning of our proof, and let's take this condition which I marked double asterisk. Let's take it. By condition double asterisk, we have this, and by injectivity, we can cancel this outer occurrence of our function. So, f of x equals x. So our function needs to be the identity function. But let's do verification. Let's do verification. Let's compare the left-hand side with the right-hand side. On the left-hand side, we have f of x plus y to the power 2n, which is, of course, x plus y to the power 2n. And on the right-hand side, we have f of x plus y to the power 2n minus 1, f of y. Well, f of x is x plus y to the power 2n minus 1 times y. It's x plus y to the power 2n. It's exactly the same. So the only solution to our equation is function the identity of this set of real numbers. And that closes our problem. Very nice problem. This condition that the preimage of 0 has exactly one element was a nice addition, because without this condition, well, Cauchy functional equation can have very pathological solutions. So it was indeed very helpful to show that our function is injective. Thank you very much for watching. I will see you next time. Goodbye.